Imagine you are analyzing data from 1,000 sensors that's located in a smart city. These sensors, they record, for example, temperature, humidity, pressure, traffic density, energy usage, and other correlated measurements. So let's say there are total 40 features. In other words, there are 40 columns. And let's say these are your data right here. X1, X2, X3, all the way to X40. These represents your 40 columns. But there is a problem. If you have too many features, then your machine learning model is going to be slow. Also, most of your features are correlated. In other words, you have redundant information in your dataset. So the question is this: is there a way to compress this high dimensional data into a smaller number of powerful features, say 4, and that still retains or that still explains most of your pattern? In other words, can you reduce the number of columns without losing important information? So can you go from here to here? Here, my number of columns is, let's say, 4. So can you go from 40 to 4 columns? And if you can, how would you do that? These are the real world problem that principal component analysis solves. Now, the feature that has the most variance in your dataset, it captures the most information that is contained in a feature space. Let's understand this statement through an example. Let's say you have a data set with columns x1, x2, and x3. This could be anything. This could be, let's say, age. X2 could be the time it takes you to go from your home to work, and this would be, let's say, the time you spend in at work. So your x1, these are the data for this: 15, 20, 10, 70, 50, 100, 60, 26. And your x2 also has some values like this. And same thing with your x3. These are all 5, 5, 5, 5. Now, if you look at your x1 right here, you will notice that it has the most variance. Your numbers, they go from 10 all the way up to 100. So the numbers are between 10 to 100. In other words, you have more spread in column x1. On the other hand, feature x2 has a moderate amount of variance. Your range are from 8 to 11. You can see 8 is the minimum and the maximum is 11. So all your numbers are between 8 to 11. On the other hand, feature X3 has zero variance. There is no spread. All values are 5. You can see that everything is 5, 5, 5, 5, 5. So there is no variance. So in other words, your feature X1, it contains the most information about our feature space. Feature X2, it contains the second most information about our feature space. And feature X3, on the other hand, it contains no information because there is no change happening in your data right here. So the more change you're happening in your data, that means the more information is present inside that column. If there is a less change in that in a data in a column, that means there is a less information present inside that column. Here, I can safely remove my column x3, my feature x3, and I would not lose any essential information in this data set. Suppose I have 4 data points shown here, and I project these 4 points on 3 different lines as shown in this picture. So this is my line 1. I'm projecting my 4 data points on this line 1. I'm projecting these 4 data points on this line 2. And I'm also projecting these 4 data points on this line 3. And you can see that the projected points on line 1 has most spread. You can see that the points are spread in a wide distance right here. On the other hand, when you project these 4 data points on line 2, well, your spread is a little bit low now. On the other hand, when you spread these, when you project these 4 data points on line L3, all your points are projected over here. There is absolutely no spread. In other words, no variance. Now, let's take a look at another set of data points, these ones right here. And now I project these points along line L1 and along line L2. So let's focus on line L1. So after I project these points on line L1, these would be my corresponding projected points. These ones, this, this, and this. And this is my spread of my projected points from here all the way up to there. This is along L1. On the other hand, when I project these on line L2, so my points would be right here. These are my projected points. Okay, and you can see that the projected point has kind of like low spread compared with L1. So the projected points on line L1, which is this right here, it contains the most information about your feature space, and the projected points along line L2, it contains less information over L1. So the direction of line 1 along the axis, that has the most variance in your data. In other words, your most variance in your data is in this direction, and your second most variance is in this direction. And this direction is determined by line L1, and this direction is determined by line L2. And these lines are called principal components. This one and this one. They capture the most variance in your data. The PC1, which is this one, this captures the maximum variance, and the PC2, which is this one, captures the second most variance. The word PC stands for principal component. So geometrically speaking, principal components, this and this, they represent the direction of the data that explains the maximal amount of variance. That is to say that these are the lines that capture the most information about your data. The relation between your variance and information is following. The larger the variance carried by a line, the more information is contained along that line. In this particular instance, the most information is contained along L1. So principal components, they are new variables that are constructed as a linear combination or mixture of the initial variables. So for example, if you have features such as age, income, experience, then your principal component would be a linear combination of your age, income, and experience. So for example, your PC1, this will be something like A1 times age plus A2 times income plus A3 times experience. Your PC2 would be something like this, maybe B1 times age, B2 times income, and B3 times experience. Same thing with your PC3. In this case, your A1, A2, A3, B1, B2, B3, C1, C2, C3, these are just numbers and they are determined during your PCA. Now, these combinations, these are done in such a way such that your principal components, your PC1, and PC2 and PC3, they are uncorrelated. And also, most of the information within the initial variable is squeezed or compressed into the first principal component. That would be this right here. This will contain the most information. The second most information would be contained in PC2, and then the third most information or variance would be present inside PC3. A side note, your principal components, they are less interpretable. In other words, you cannot think of them as age or income or experience the way you think of them as a normal columns. They don't have any real meaning because they are constructed as a linear combination of your initial variables. So how many components should we select in PCA? Well, let's answer this question by looking at an example, the breast cancer dataset. So first I'm doing is importing my library right here, importing my pandas SPD, NumPy, and all the other libraries. I'm also importing my scikit-learn. And from my scikit-learn, I'm importing my PCA. This is responsible for performing principal component analysis. First, I read my data. There's a breastcancer.csv. I read that data and I'm printing first few records. So it has these columns, mean radius, mean texture, mean parameter, and you can scroll down. It has many, many features. There are 31 columns in total. Out of these 31 columns, there is one column that is target column. We would not be using that in our feature space. We would be using all the columns except the target columns. So what I'm doing, I'm just dropping the target column and I'm taking all the rest of the columns over here. My target column, I'm just calling it y. I'm just putting all the values of my target column inside variable y, and then I'm printing the first two values just to show you what the records are. So these are my first two values. So this is my first record right here. and this is my second record. In other words, these are my two data points. And you can see there are 31 or 30, as a matter of fact, there are 30 values in here. 1, 2, 3, all the way up to 30 right here. Okay, now let's apply PCA. Step 1. You want to make sure you standardize your data. So in this case, I'm using standard scalar. I'm feeding my X to that. X is my feature space. It creates an X scaled feature space. Then I'm printing my first two records of my feature space. And these are my first two records. So my first record, if you recall, was this right here. These numbers now have been turned or scaled into these numbers. Okay, step 2. Now you find the variance of each principal component. For that, you call PCA equal to PCA. That's what you do. That's all. This is your small PCA. And then you call inbuilt method called as fit transform. Pass in your X scaled, which is this value that you just created a minute ago. Okay. And then you find out your explained variance ratio. I'm rounding off by 3 digits and I'm printing my explained variance ratio. So in this case, the first principal component, it explains 44.3% of your variance. The second principal component explains 19%, and the third explains 9.4%, all the way up to over here. That would be your 30th principal component. Now, I want to visualize this result. So I'm visualizing this result. This code, that's what it does. Come down. And this one tells me right here, principal component number 1, it captures 44% of my variance. Component number 2, it captures 19%. And same thing with 3, 4, 5, 6, 7. So all these numbers right here, I'm just plotting them in this way using this bar graph. Okay, now let's plot the cumulative sum. I want to see the cumulative sum. So I do my cumulative sum and this one tells me principal component 1, it captures 44.3%, and principal component up to 2, including 1 and 2, it captures 63.3. Okay. Principal component up to 3, meaning 1, 2, and 3, it captures 72.7%, which is this right here. Right here. Principal component up to 4, that captures 79.3% of your variance. That would be this right here. And you can keep going like this. So as your principal component increasing, the amount of the total or the cumulative variance is capturing is increasing. Step 3. Now you identify the right number of components you need. Well, 10 seems to be a good number. If you look over here, 10 is this number. That's capturing approximately 95% of your variance. So your 10 is this right here. This one is your 10th principal component. This is up to 10 principal component, and this is capturing 95% of your variance. So 10 seems to be a good number. So now I create my PCA with number of component equal to 10, and then I'm creating my new scaled features that actually takes into account principal component. Okay, now I'm printing my original data points, and I'm also printing my new data point in 10 dimension. My original data point was in 30 dimension. So this is my original data point right here. You can see it has 30 dimensional data point. And now my new data point for this particular one data, it is in 10 dimension. You can see your data has been reduced from here to here. Very good. And now the final step, step 4. I'm going to work with this new data set now. I'm not going to work with my original X. So my original X now, I'm replacing it with xpca underscore 10d. My original X contained 30 columns. Now this is going to contain only 10 columns. So to recap, what we did was this. We had a breast cancer data set that had 30 features and one target column. We applied PCA to feature columns only, not to the target. So first find all 30 principal components. Then you select the top number of components that would explain the maximum amount of variance. So in our example, the breast cancer data set, there are 30 features. Now from the graph, we can see that your principal component 1 is 44.3% variance. It contains 44.3% variance. Principal component number 2 contains 19%. Principal component number 3 contains 9.4%, and so forth. So it seems like 10 principal component that would explain 95% of the total variance in your data. So 10 component, it might be a good number, and that's why we picked up 10. This way, we reduced our number of columns from 30 to 10. A side note, alternatively, we can plot the cumulative variance and read the number of components you need based on the variance required. So let's say you need 86% of the variance. So your 86 will be somewhere over here. So you just come and read and you say, okay, that's going to be 5. So I'm going to work with 5 component because I need 86% variance. Well, maybe you want 95%. So your 95% would be somewhere over here, and just come and look over here. Your 95 is going to be maybe 9 components, or maybe it could be 10 components. So if you're dealing with 95% and you choose to have 10 components, you are going to work with the 10 components.